Hello my dear friends, welcome back to my YouTube channel. In this class I am going to discuss some PYQs of GATE, that is previous year questions, and their solutions I am going to discuss of GATE on refrigerator and heat pump. I just finished a series of lectures in which I discussed each and every bit of the problems of chapter 6 of PYQs Engineering Thermodynamics, which were obviously based on second law and refrigerator and heat pump. So now I am going to solve some PYQs of both GATE EXE and GATE ME as well as the GATE PI also. The questions of refrigerator and heat pump were asked in the exams. So before starting, I must say one thing to all of you. Please do subscribe to this channel. Of course, like it and share it to your friends. Let's get started. You see, the first question was asked in the GATE 2021 XC, and the question was like this: for a refrigeration cycle, the ratio of actual COP to the COP of a reversible refrigerator operating between the same temperature limits is 0.8. Obviously, we know that given between two given temperature limits, the COP of a reversible refrigerator is the maximum one, and the actual refrigerator will be having COP definitely less than that reversible refrigerator. That's why the ratio is 0.8 actual COP to the COP of reversible refrigerator. The condenser and evaporator temperatures are 51 degrees Celsius and minus 30 degrees Celsius. 51 degrees Celsius and minus 30 degrees Celsius respectively. You know, in a refrigerator, the condenser and evaporator temperatures, you can say, are the TH and TL. This is the higher temperature and this is the lower temperature. So you can say TH is 51 degrees Celsius. Of course, you have to convert that into Kelvin by adding 273 to it, and TL is minus 30 degrees Celsius. If the cooling capacity of the plant is 2.4 kilowatt, if the cooling capacity, that means the capacity to remove heat, and that is the that happens in evaporator, then the power input to the refrigerator is how much? Then the power input to the refrigerator is how much? The options are 1 kilowatt, 1.33 kilowatt, 2.08 kilowatt, 1.25 kilowatt. You see, this is obviously not a reversible refrigerator because the ratio is 0.8. The COP of this actual COP of this refrigerator, ratio of actual COP, this line is important, the ratio of actual COP to the COP of reversible refrigerator. So suppose let TH be the higher temperature, and obviously this is in terms of Kelvin, this is 273 plus 51, 273 plus 51, that is 324 Kelvin, 324 Kelvin, and TL is obviously, that is minus 30 degrees Celsius, is equal to 243 Kelvin. This is actually the condenser temperature and this is actually evaporator temperature. Suppose the refrigerator is operating like this, it's an anti-clockwise device, and this is the, suppose, Q dot L. This is the actually heat removed in the evaporator, heat removed. So this is the Q dot L, and this is actually Q dot H, heat rejected to the surroundings in condenser, and suppose this is the W dot, the power input, W dot. According to the given data, you see the COP actual divided by COP reversible COP of actual refrigerator. In fact, in case of refrigerator and heat pump, COP, coefficient of performance, is calculated. There is no term called efficiency in these devices, is 0.8. So that means, you see, I can write like this: COP of actual COP of this particular refrigerator is equal to COP of reversible refrigerator. Actually, COP of reversible refrigerator is nothing but TL divided by TH minus TL. That is TL divided by TH minus TL. This is the COP of. From this, I can write COP of actual refrigerator is COP of reversible refrigerator multiplied by 0.8, and this is equal to 0.8, and this is equal to 324 divided by 324 minus 243 multiplied by 0.8. This is equal to this TL is nothing but 243, and this is TH is 324 minus 243. This is equal to 243 divided by 81 into 0.8. This is the actual COP. We know that the actual COP, this is equal to, this ratio is 3 multiplied by 0.8, it is 2.4. So actual COP will be 2.4, and actual COP is nothing but Q dot L divided by W dot. Q dot L is given. Q dot L is 2.4 kilowatt. So Q dot L, the cooling load, the rate of heat removed, Q dot L divided by W dot in is actual COP. COP is nothing but desired effect by work input, that is Q dot L divided by W dot in is equal to 2.4. But Q dot L is given. Q dot L is 2.4 kilowatt. So 2.4 kilowatt divided by W dot in is equal to, your COP has come out to be 2.4. So now equating this, we will get W dot in is 1 kilowatt. 2.4 kilowatt and this is 2.4. So obviously W dot in will be 1 kilowatt. So that is the option A is the correct answer. Option A, 1 kilowatt. Since the actual COP has come out to be 2.4 and actual COP of refrigerator is desired effect by work input. So desired effect is your cooling load, that is rate of heat removal 2.4 kilowatt, that is given. So 2.4 kilowatt in place of Q dot L I will write 2.4 kilowatt divided by W dot in is equal to 2.4, that is the actual COP we have calculated. So that means W dot in is nothing but 1 kilowatt. So option A is the correct answer. Next question is, you see a refrigerator working on a reversed Carnot cycle has a coefficient of performance of COP of 4. You know, COP of refrigerator between two given temperature is 4. If it works as a heat pump and consumes work input of 1 kilowatt, then the heating effect will be how much? You see, we know that COP of heat pump, and this was asked in the year 2021 ESE GATE. So COP of heat pump is nothing but COP of refrigerator plus 1, and COP of refrigerator is given to be 4. So that is 4 plus 1. 4 plus 1, that is equal to 5. And COP of heat pump is nothing but, suppose this is the TH, higher temperature, this is the TL. this is heat pump, this is the QH, this is the QL. The same figure done here. You see, COP of this heat pump will be Q dot H divided by W dot, Q dot H divided by W dot, and for refrigerator it will be Q dot L divided by W dot. So here heating effect is required to be found out. Heating effect is nothing but Q dot H, and consumes work input of 1 kilowatt, that is W dot in is W dot in, that this is the COP, and we have calculated the COP of heat pump is 5, because you know COP of heat pump is always greater than COP of refrigerator by 1. So Q dot H divided by W dot in is equal to 5, and Q dot H, W dot in is given to be 1 kilowatt, is equal to 5, means Q dot H, that is the heating effect, will be 5 kilowatt. 5 kilowatt. From the given options, obviously 5 kilowatt, option A is the correct answer. 5 kilowatt. COP of refrigerator is given, and heating effect has been required to be found out, and work input is given to be 1 kilowatt. You know, COP of heat pump is always greater than COP of refrigerator by 1. So since COP of refrigerator is 4, COP of heat pump will be 5, and COP of heat pump is nothing but the heating effect divided by work input, and in case of refrigerator the COP is cooling effect divided by work input. So from this, since work input is given to be 1 kilowatt, then Q dot H is calculated to be 5 kilowatt. This is the heating effect. Next question, question number 3. Question number 3. You see, if a reversed Carnot cycle operates between the temperature limits of 27 degrees Celsius and minus 3 degrees Celsius. Reverse Carnot cycle operates between 27 degrees Celsius and minus 3 degrees Celsius. Then the ratio of the COP of refrigerator to that of heat pump based on the cycle is dash. Round up to 2 decimal places. And this question was asked in the GATE 2020 mechanical engineering. You see, suppose the higher temperature is TH and the lower temperature is TL. Higher temperature is TH and the lower temperature is TL. Obviously, since this is suppose the refrigerator, and the same refrigerator can also act like heat pump. You see, the direction of heat flow is like this. This is the W, this is QL, and this is suppose QH. You know, COP of reversed Carnot refrigerator. You know, COP of reversed refrigerator, that is the refrigerator working on reversed Carnot cycle, will be COP of reversed refrigerator is TL divided by TH minus TL. That we know. And COP of reversed Carnot, actually Carnot heat pump, is equal to TH divided by TH minus TL. So if you calculate the ratio of COP of refrigerator to that of a heat pump, so this divided by this will obviously be, so this divided by this will be nothing but TL upon TL upon TH, and this is low temperature is minus 3 degrees Celsius. So in terms of Kelvin, this is 270 Kelvin. Obviously these are temperatures expressed in Kelvin. So lower temperature is given to be minus 3 degrees Celsius, means this will be 270 Kelvin divided by higher temperature is 273 plus 27, that is 900, sorry 300. So 270 divided by 300, that is 0.9, 0.9. So that is 0.9. The answer is 0.9. So next question is question number 4. This was asked in GATE 2020 XC. So the relation between the COP of refrigerator and COP of heat pump. This I have already discussed through this lecture, that is COP of heat pump is always greater than COP of refrigerator by a magnitude of 1. So out of the given options, obviously this one is correct. Option A is the correct answer, that is COP of heat pump is greater than COP of refrigerator by a magnitude of 1. So option A is the correct answer. Option A is the correct answer. This question is quite easy. Option A is correct answer. So always COP of heat pump is between two given temperatures, be it reversible or irreversible. COP of refrigerator, if you have calculated, then COP of heat pump can be calculated to be 1 plus the COP of refrigerator. So question number 5. Question number 5. You see, question is like this. A heat pump is to supply heat at the rate of 10 kilowatt to a building to be maintained at 22 degrees Celsius. The room is to be maintained at 22 degrees Celsius. That is in terms of Kelvin, 273 plus 22, that is 295 Kelvin. This is TH. And the surrounding is outside is at 2 degrees Celsius, that is 275 Kelvin. The minimum power in kilowatt required to run the heat pump. In winter, when the outside temperature is quite low and you want to maintain the temperature of your room at a higher level, obviously since the temperature of room is high, means heat will always flow from your room to surrounding. So to maintain the temperature at that particular level, you have to continuously supply heat to the room. So that has to be done by the same components that constitute the refrigerator, and in winter they will act like a heat pump. So suppose this is heat pump and this is Q dot L, this is Q dot H, and this is W. But you see, a minimum power you have to find out. So minimum power, COP of heat pump is Q dot H divided by W dot in. So minimum power, since this is constant, to maintain the room temperature at 22 degrees Celsius, obviously you have to supply 10 kilowatt. This 10 kilowatt is there. Q dot H is 10 kilowatt. So this is 10 kilowatt divided by W dot in. So obviously minimum work input is required only when the COP is highest. From this expression, this 10 kilowatt is fixed. So COP, how can the W be at its minimum level? Only when the COP is highest. And the COP of heat pump is highest when it acts on reversed Carnot cycle. So the COP of reversed Carnot cycle we have already discussed is 295 Kelvin divided by 295 minus 275 Kelvin. that is 295 divided by 20. 295 divided by 20 is equal to 10 kilowatt divided by W dot. This W dot is the minimum work required. By equating this 295 by 20 is equal to 10 divided by W dot in, that is I can say W dot in is equal to 200 divided by 295 kilowatt, and on rounding it up to 2 decimal places it comes out to be, in fact it is 0.677, and by rounding it up to 2 decimal places 0.68 kilowatt. This is the power required. So next question is question 6. Question 6. You see, the figure shows a heat engine working between two reservoirs. The amount of heat Q2 rejected by the heat engine is drawn by the heat pump. This is the important line. The amount of heat Q2 rejected by the heat engine, that is, this is the amount of heat rejected, Q2. The amount of heat rejected by the heat engine is drawn by the heat pump. Whatever heat is rejected, and this temperature is, you see, this temperature is, this is T2. You see, the heat pump receives the entire work output W of the heat engine. So whatever work is produced by this heat engine, that goes on to drive the heat pump. You know, heat pump is a work consuming device, and if temperatures are like this, T1 is greater than T3 and T3 is greater than T2. You know, T1 is always the highest temperature, because this is the high temperature from which heat is extracted by heat engine, and T2 is the low temperature to which it is rejected. And again, you know, heat pump transfers heat from low temperature to high temperature. Obviously T3 will be higher than T2. So the relation between the efficiency of the heat engine and the COP of the heat pump, relation between the efficiency of the heat engine and the COP of the heat pump is, we have to find out. You see, the efficiency of the heat engine is, work output divided by Q1, W divided by Q1, and COP of heat pump is Q3 divided by W, Q3 by W. You see, Q3 is nothing but Q2 plus W. You see, by applying energy balance equation to this cyclic device, you know, in case of a cyclic device, summation of energy that enters into system during a cycle is equal to summation of energy leaving the system during that cycle. Here the energy leaving is Q3 and these energies are entering the system, Q2 plus W. So Q2 plus W is Q3. So I can write this COP of heat pump as Q2 plus W divided by W. And you see, in case of heat engine, efficiency is W by Q1. And applying the energy balance equation to this heat engine, I can write Q1 minus Q2 is equal to W. The only energy that enters into heat engine is Q1, and these two energies leave the system during the cyclic process. So Q1 is equal to Q2 plus W. So this, in place of Q2 plus W, I can write Q1 also, Q1 by W. So you see, efficiency of heat engine we have calculated is W by Q1, and COP of heat pump is Q1 by W. Where does this come from? Q1. Why I wrote Q1 in place of Q2 plus W? Just by applying the energy balance equation for this system undergoing a cyclic process. Summation of energy is entering the system during a cycle is equal to summation of energy leaving the cycle. So Q1 equal to Q2 plus W. So in place of Q2 plus W, I will write Q1 by W. Now things are clear. You see, efficiency of heat engine is W upon Q1, and COP of heat pump is nothing but Q1 upon W. So that means COP is equal to, out of the given options, this option is correct, because COP is the reciprocal of efficiency, or efficiency raised to the power minus 1. Efficiency raised to the power minus 1 matlab COP is equal to 1 by efficiency, and this is what we have found out. So COP is Q1 by W and efficiency is W by Q1. So out of the given options, obviously the option B is the correct answer. So option B is the correct answer. That's all. Thanks for watching.